Hello. Now, in this lecture, we will study the laws which gives the direction of induced current. The first law which gives the direction of induced current and we are going to discuss is Fleming's right hand rule. When we stretch the thumb, forefinger and the central finger of our right hand in such a way they are mutually perpendicular to one another and forefinger points in the direction of the magnetic field. Thumb points in the direction of motion of the conductor. Then central finger will give the direction of induced current. It is a Fleming's right hand rule which is also known as motor rule or the generator rule. Now the Lenz's law. According to the Lenz's law, the direction of induced current is such that it opposes the chain that is producing it. We will discuss or explain it later on. First, let us look at the alternative definition. The second definition or the statement of the Lenz's law is the polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Now let us understand what is meant by the Lenz's law. It is a coil and it is the magnet. When we move the magnet towards the coil, that is we are moving the north pole of the magnet towards the coil, then the polarity in the coil develops in such a way that it opposes the motion of the magnet towards itself, and it is possible only when the north pole develops at this end. When the north pole is developed, then due to the force of repulsion, magnet is not moving towards the coil. That is the Lenz's law. According to Lenz's law, the induced EMF develops in such a way that it opposes the cause, it opposes the changes that is producing it. The current is produced due to the motion of the north pole towards itself. So the direction of the current is such that it opposes the motion of the magnet towards the coil. Similarly, if one is taking the magnet away from the coil, as the magnet is going away from the coil, then the polarity develops at this end. Should be current flowing in the coil is such that the south pole develops at this end. When the south pole develops due to the force of attraction, it opposes the motion of the magnet away from the coil. So I think you will understand the Lenz's law. Now see, when we move the magnet, north pole of the magnet towards the coil, then the north current flows in such a direction, in such a way that the north pole is developed at this end. Now to make it more clear, let us take more example. Now it is a coil, and when the circuit is completed, when we insert the key in it, when we press the switch, then circuit is complete and the current is flowing. The current takes some time to become constant. As we press the key, the current begins to flow from 0 to its constant value. And for that moment, the current is not constant. And you know very well that the magnetic field inside the coil is given in this way, where N is the number of turns per unit length and I is the current through the coil. If this current is variable, then the magnetic field is variable, and if the magnetic field is variable, then the flux linked with the coil is variable. And if the flux linked with this coil is not constant, then this flux can produce the current in the neighboring coil. Now see, it is a neighboring coil. it is a coil, okay? And when the flux linked with the coil P increases, then the direction of the current in the coil S is such that it opposes the increase in current in coil P. Means it flows in opposite direction. If the current in the coil P is in clockwise direction, then in this coil it should be in anti-clockwise direction. Now see, circuit is completed. Circuit is completed. Direction of the current is reversed. Here it is in clockwise direction and here it is in anti-clockwise direction. Now the second case. It is a coil P and S. Now when we break the circuit, again when we break the circuit, the magnetic field varies. If the magnetic field varies, the flux varies. If the flux linked with the coil P changes, then as a result the flux linked with the coil S also changes and current is flowing in the coil S. And according to Lenz's law, direction of the current is such that it opposes the decrease in flux in coil P. So the direction of current in both the coil is same. If in this coil it is in clockwise direction, then in this coil also it is in clockwise direction. One point. Second point, current will flow in this coil only for the time the flux linked with the coil is varies. When it is constant, the current flowing through this coil, current flowing through the coil S stops. See, it is in the same direction as the current constant. The current in this coil stops. Now one more time. As the circuit breaks, the current in both the coil is in clockwise direction. Now, what will happen if instead of the closed circuit is open? It is not complete. In that case, instead of the current, EMF is induced. Now, suppose here when we are taking the north pole of the magnet towards the coil, north pole is not formed. Instead of the north pole, the south pole is formed. In that case, there is a force of attraction and a little push to this magnet results in an increase in the kinetic energy without expending any energy. And it violates the law of conservation of energy and hence it will not happen. Means we can say that here only the north pole is formed when we are taking the north pole of the magnet towards the coil. Now consider the correct case. When we are taking the north pole of the magnet towards the coil, then the north pole is formed. And as a result, one has to do work against the force of repulsion in taking the magnet towards the coil. And this work done is converted into the electrical energy. Similarly, when the one take the magnet, north pole of the magnet away from the coil, south pole is formed and one has to do work against the force of attraction. And this work done is converted into the electrical energy. Lenz's law is in accordance with the law of conservation of energy. Thank you and have a nice day.